Okay, I'm going to talk about some prerequisites today. There's some topics we have to get to before we actually get into the calculus. Today we're going to talk about graphs and models. I think you'll find most of this stuff is pretty review, just some things we want to make sure we have our bases covered before we move on. Okay, so graphs and models, basically a big part of this class, as you probably could guess, is to graph things and to model certain situations using graphs. The first thing we're going to start very basic, and that is sketching and plotting points. Okay. Okay, so when we sketch and plot points, we don't want to lose sight of what's actually happening. So let's just take a very basic equation right here. So let's say we have y equals x squared plus 1. Okay, and we're going to plot the points old school here. So we're just going to do a table of values. By the way, this is probably the most inefficient way to graph this. So anyways, you guys should all know how this works. I'm going to take these values of x, plug it in here to this equation, and I'm going to get y values. So I get 5, 2, 1, 2, and 5. Okay, now we should realize that this particular equation is going to have an infinite number of possible pairs of x and y. What we're doing when we're graphing is sort of giving us a pictorial view of these infinite possibilities, because of course you can't list them all out because there's an infinite number of them. And that's really what a graph is. It gives us kind of a pictorial representation of something that really has infinite possibilities here. So let's just do a quick sketch. By the way, in this class, unlike maybe some of the classes you've had in the past, graph paper really isn't important. Rough sketches in this class for the most part will work as long as we're showing the big details. So you can save yourself some money and not get graph paper unless you really, really like to use graph paper. Okay, so -2 and 5, -1 and 2, 0 and 1, 1 and 2, and 2 and 5. And that, of course, is a parabola. And plotting points kind of gives us an exact idea of what's happening here. We're plugging in values of x, getting out values of y down the line, and actually you have a lot of techniques already. You probably didn't need plot points to be able to graph that. There's a lot of different ways to do this that is a lot easier than just plotting points. Okay, the next thing I want to talk about is one thing in this class is we have to be very careful. I would say in general, plotting points is not a great way to graph in general in this class. It kind of gives us an idea of what's happening. So for instance, let's take another equation you should know well and just think if I just plotted a few points, I might have the wrong idea. So let's go with y equals x to the third. So just forgive me because we know that this kind of has a curvy shape, but let's say we were just plotting 3 points here. Okay, and what we could maybe convince ourselves, because if we just look at those 3 points, it looks like this graph is going to be linear, right? So if I graph this, I might think that, oh, this is a line. By the way, this is wrong, obviously, because we know that there's curving in here, and then also this goes up. So we can quickly sort of fix this by realizing that if I add a few points, let's just add 2 more, -2, that would give us 8, and 2, that would give us 8. Then we get something that clearly is not linear. we get a cubic function, which kind of has a bit of a curve like this. Okay, so this would be the correct representation of this. So one thing we want to keep in mind is if we are plotting points, that we're looking at enough points to get a feeling for the shape. Okay, this obviously is one that is pretty simple here. Another thing that is going to come up in this class quite a lot is a big focus is sometimes we're not given an equation. Sometimes we're not given an equation. Sometimes we are just given a table of values. And this kind of fits into what I was just saying here with the cubic. Let's say we didn't know what the cubic looked like. And let's say I got values like, let's make it really basic, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. And let's say the values we get here are -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5. So let's say I give you this and I say, this is our function. This is our equation. And you're like, oh, well, I know exactly what that equation is. I know that that is the line y equals x. So here's the thing. It may be the line y equals x, but we don't actually know. So we actually don't know that it is or is not that. You're saying, look at all those values, it has to be that. It's the only equation that fits that. Sometimes we're not going to have things defined by equations. So what actually, it's possible that they're just not telling us all the information, and actually something between here, let's say -4.5 is actually 18. This thing jumps up to here all of a sudden. Okay, so just kind of a drastic point, but don't assume if we're given values on a table that we actually know the values in between, unless we're given an equation that we can check. Okay. Now, as far as the graphing calculator and doing graphs with that, I am going to talk about that in class. I just think it'll be easier to do that in class, where I have access to a projectable version of the graphing calculator. For this stuff, we're just going to do this stuff by hand. Okay. So the next thing I want to talk about forgive me, takes a while to erase this stuff. Okay, so let's talk about intercepts. So we're talking about intercepts of the axes. Okay, so let's just take a look at a graph here. And no equation here, just a graph. Okay, so we have this point here, which is -3, 0. This point here, which is 0, 2. This one here, which is 5, 0. Okay, so those are our three intercepts. Namely, we have two x-intercepts. By the way, when you label x-intercepts, always show it in this coordinate pair. So the x-intercepts will always have the 0 for y, of course. So this will be -3, 0. And 5, 0. Y-intercepts. Y-intercept, we have one y-intercept, and that is 0, 2. This marker looks like it's dying on me. Okay, so nothing new there, x and y intercepts. Let's move on to doing this using an algebraic equation. So once again, we're going to do this without a calculator. Sometimes you'll have use of your calculator, sometimes you won't. If you have use of your calculator, you can use those features which once again, I'll show you that in class. But if we don't have our calculator, then we have to do this algebraically. So let's say we want to find the x and y intercepts for the equation y equals x squared plus x minus 2. Okay, so first of all, let's do the x-intercept. Now, x-intercept, keep in mind, if we're crossing the x-axis, right, as we saw before, all those points are going to have y equals 0. So algebraically, we can simply just let y equal 0. So let's plug the 0 in. We get 0 is equal to x squared plus x minus 2. Now, it's probably been a little while since you've done this, but we're going to solve this quadratic for 0. The easiest way to solve a quadratic, if it factors, is to factor it. Otherwise, you have to go to like the quadratic formula. Which usually, what I'll say is usually when we don't have use for our calculator, usually they will factor. Not always. We do still sometimes have to use a quadratic formula, but that is less common. So this one does factor. Okay. Yes. Okay. So now what this means is we have two things multiplied together that equals 0. So we use the old zero product property. So what the zero product property tells me is if I have multiple things multiplied together that give me 0, at least one of them has to be 0. Okay? So either x plus 2 is equal 0 or x minus 1 is equal 0. So then we get x equals negative 2 and x equals 1, and those are our x-intercepts. Once again, when we label our x-intercepts, we want to do it as a coordinate pair. So negative 2 comma 0 and 1 comma 0 are the intercepts. And there you go. Okay. So let's find the y-intercept now. Actually, the y-intercept is going to be easier. So of course, for the y-intercept, if I let y equal 0 to get the x-intercept, I'm going to let x equal 0 to give us the y-intercept. So y is equal to 0 squared plus 0 minus 2. Very easy math here. We get y is equal to negative 2. So my y-intercept is 0, negative 2. Okay? And that is how we find x and y intercepts without a calculator. In class, I'll show you how to do this with a calculator. Okay. Obviously, in a case like this, this one's pretty easy. It's probably faster to do without a calculator anyways. Next thing I want to talk about is if we want to graph this, plotting points is going to be kind of annoying. However, if I find the x and y intercepts, we can come up with a really quick sketch, a really good look at what this thing looks like without spending all that time plotting points and maybe missing a point. This is going to give us a big feature, especially because we do know this is a parabola that opens up. Without getting into a lot of details here, I'm not even going to bother finding the vertex or anything right like that for this right now. So I have the y-intercept is 0, negative 2. And I have the x-intercept, negative 2, 0, and 1, 0. Now we can see as the parabola opens up. We know that the vertex is going to be somewhere equidistant between those 2 points without finding exactly what that y is. I know the x is going to be actually x equals negative 1/2. So let's not worry about exactly where that is on the y. We get a pretty quick sketch without worrying about plotting all those points. Okay, so those are intercepts. Okay, so let's move on to talking about the symmetry of graphs. Okay, now right now one thing I want to talk about is down the line, a lot of our focus in this class is going to be on functions. So if you remember functions, and we'll talk more about that in the prerequisites, functions of course have an input and one output. So graphically, they pass the vertical line test. Right now, we're not necessarily talking about functions. We're just talking about any equations, whether they're functions or not. Okay. So let's talk about these symmetries. Where's that marker? The negative marker. So symmetry of a graph. There's actually 3 symmetries that we're interested in. There is x-axis symmetry. Okay. 2, there's y-axis symmetry. Y-axis symmetry. And 3, there is, and this is the one that will confuse some folks, symmetry to the origin. Okay. So let's just talk about, I'll give you 3 examples of these graphically, and then we'll talk about what that means exactly. So let's talk about x-axis symmetry. Basically, that means if you put a mirror on the x-axis, right, it looks the same, right? It reflects over the x-axis. Obviously, this is not a function, okay, because it's failing the vertical line test. So what happens when we have x-axis symmetry? So what happens is for the same x value, right, we're getting opposite outputs. So for instance, if this is y, this would be negative y. And that's important to understand that because we're going to use that to test these things algebraically later. Okay? So basically the same x input, we get opposite y outputs. Y-axis symmetry. Okay. So y-axis symmetry, sticking with parabolas a lot today. So y-axis symmetry would be like something like that. So it's reflecting over the y-axis. Now with y-axis symmetry, okay, for opposite x values, so call that negative x, call that x, we're getting the same output, the same y. So this would be y negative, or excuse me, x, y, and this would be negative x, negative y. Excuse me, negative x, positive y, same, not opposite. Getting ahead of myself. Okay, so this would be negative x, positive y. All right, origin is the one that throws people off the most. Origin is like a diagonal symmetry, so if you think of sort of your standard cubic, 1 over x type thing, this would be symmetric to the origin. So let me just do a couple of examples here because this is the one that seems to throw people off the most. Okay, so it's kind of diagonal symmetry, okay? The easiest way to think about this one is that it's kind of a reflection on, if you take this graph and reflect the y and then reflect the x, it reflects back into itself. So if you think about reflecting this over the y and then the x, it reflects back into itself. Now what it means in terms of what I'm talking about here is if we look at like the opposite x values. So x and negative x. The opposite x values have the opposite outputs as well. So for instance, this point we would call x positive y, and then this point right here we would call negative x negative y. So like I said over here, I was already writing and I was getting ahead of myself. So for instance, this point right here, we would call this x y, and then this point over here we'll call negative x negative y. Okay? So that is symmetry to the origin. So now, how do we test these things? How do we know if something is symmetric to the x-axis, the y-axis, or the origin algebraically? And one thing I want to caution you against is never rely on the graphs in these cases. The reason why is if you think about it, if I move this graph over just slightly, right? If I just shifted that like 0.001 to the right, it would look like it has y-axis symmetry, but it wouldn't have y-axis symmetry. So it's always important when we're testing symmetry that we actually look at the algebra. And what we're going to use is these points I talked about. So let me just review that. Okay, so for instance here, x-axis symmetry means the point xy is going to be equivalent to the point positive x, negative y. Okay, y-axis would be the point xy is going to be the same as x negative x positive y. And origin would be the point xy is going to go to negative x negative y. And this is what we're going to use to test these things. So we're going to do two examples here so you can see how this works. So let's say I give you the equation y equals x to the third plus x. How is this thing symmetric? Okay, so the first thing I'm going to do is I'm going to plug in negative x. So everywhere I see an x, I'll plug in negative x. And then I want to simplify this. So what happens here, of course, is if I take negative x to an odd power, it's going to end up retaining that negative. So this one I can simplify as y equals negative x to the third minus x. So notice it's not the same as the original, right? If this was the same as the original, then we'd have y-axis symmetry because the negative x would give us the same, okay? So this is not, we do not have y-axis symmetry. So how do we test to see if we have x-axis symmetry or to the origin? In this case, we're going to plug in negative y. So the first thing I'm going to do is plug in negative x. The next thing I'm going to do is I'm going to plug in negative y. So everywhere I see a y, I'm going to plug in negative y. Okay, now I want to simplify it so it looks like the other thing. So of course what I'm going to do here is multiply both sides by the negative. And that's going to give me y equals negative x to the third minus x. So what I realize here is plugging in negative x gives the same as plugging in negative y. What that means in that case is that this one is symmetric to the origin. And that's how we test it. And if you're asked to test, this is what I want to see. I want to see you plugging in the negative x. So once again, let me remind you how this works. You plug in the negative x, simplify it. If it's equal to the original, that means it's symmetric to the y-axis. Okay, it's not here, so it's not symmetric to the y-axis. Then I'm going to plug in negative y. Okay, simplify that. If the negative x plugged in and the negative y one are plugged in, give us the same thing and symmetric to the origin. All right, let's look at a problem that has multiple symmetries. Okay, so let's go with x squared plus y squared is equal 4. So you might recognize this as being a circle. If you think of a circle, you can see why we're going to have multiple symmetries here. Okay, so the first thing we're going to do is plug in the negative x. So everywhere I see an x, I'll plug in negative x. Now, in this particular case, okay, negative x squared, that's an even power, that's going to stay positive. Okay, so what we see is this is actually equal to this. So this is equal to this, that means that this is symmetric to the y-axis. Okay, so y-axis symmetry. Now we're going to plug in negative y. So everywhere I see a y, I'll plug in negative y. Okay, so of course I get x squared plus y squared is equal 4. This is equal, so this is equal to that. So that means that we have x-axis symmetry. But I also want to point out that since this, like the last time, right, this is equal to this, we also have origin symmetry. And once again, we all know that this is because this is a circle with radius 2, centered at the origin. So we can see it has all the different symmetries that we would be interested in here. Okay, so that basically does it from symmetry. Once again, I just want to stress that if you're using your graphing calculator here to tell symmetry, you can be easily fooled, so be careful with that. Okay, I want to do one last example, and that's going to be doing a graph. And I did do one example of this already, but I want to do another example of graphing something based on the x and y intercepts and symmetry. So we're going to basically do those two things, and then we're going to use it to graph. Okay, so let's go with the equation. X plus y squared is equal 3. Okay, so the first thing is we're going to do the x and y intercept. So x-intercept, we let y equal 0. So x plus 0 squared is equal 3. So here we get x equals 3. So our x-intercept is 3, 0. Y-intercept, that is going to be, plug in x, 0 for x. Oops. Okay, now we get y squared is equal 3. It's important to realize that if we have this y squared, if we take the square root, we're going to get a plus or minus. So we're going to get y is equal to the plus or minus square root of 3. Now, I don't know exactly what that is, nor do I care. I know that this is somewhere between 1 and 2, right? Because square root of 1 is 1, square root of 4 is 2. So somewhere between 1 and 2, the detail, exactly how far along, is not all that important here. So we have 0, negative square root of 3, and 0, positive 3. So we have two x-intercepts. Okay, now what I'm going to do is I'm going to do the symmetries. So once again, let's plug in negative x for x. Okay, so let's simplify that. That's negative x plus y squared equals 3. Those are not equal, so it is not symmetric to the y-axis. So now I'm going to plug in negative y. Everywhere I see a y. I'm squaring that. Negative y squared is going to give us a positive. This is equal. So what that means is that I have x-axis symmetry. If these two things are equal, which they're not, we would have origin symmetry, which we don't. Okay, so now let's take a look at graphing this just from that information. Okay, so first of all, let's graph these points. 1, 2, 3, 0. There's my x-intercept. Y-intercept. 0. And like I said, I don't care how close this is, just somewhere between 1 and 2. And finally, what I realize is since this is symmetric to the x-axis, what we have is sort of a sideways parabola. So to the best of your ability, sort of make it look symmetric. And there you go. So that's a quicker way to graph there. I don't have to go through plotting all those points. All right, so that is prerequisite section number 1. All right.